4 must-know ML concepts. Whether you're a student, a data scientist, or engineer, this video will serve as either a refresher on the basic fundamentals or simply a way to bridge the key concepts together. Instead of talking about each concept independently, I'll bridge them together like a story. Let's get started. The first is training. It can be really annoying when people talk about models learning or training without being clear as to what that means. So let's start off with a high-level explanation, and later in the video, we'll talk about the actual equation used for training. Over some number of iterations, we adjust the model and improve its performance. Let's say our model learns to predict how tall someone will be from a dataset where we have various information about people, as well as their final height once they're finished growing. How do we actually increase the model's accuracy? Well, we need to remind ourselves of what a model is. It's just a mathematical formula that outputs a prediction. There's two components to the formula. First, the inputs that might affect someone's final height. This might be their current weight, their current height, and the average of their parents' heights. Second, the parameters. They're also called weights. Let's look at the simplest kind of ML model, represented by this equation. The input numbers are x1, x2, and x3, while w1, w2, w3, and b are the parameters of the model. The parameters are just random numbers at first, so the output number h won't be a very accurate prediction of how tall someone will be, but over training, we update the values of the parameters, improving the model's accuracy. And that's all training is. We're just adjusting the parameters of the formula. LLMs, for example, are also just large math formulas. They are formulas that predict the exact sequence of words that best answers your prompt. The formula is a lot more complex since we're dealing with words, and before we pass words into a math formula, we have to represent each word as a number. And then when numbers are outputted by the LLM, we have to convert them back into words so that we can actually read the response. But at the end of the day, a large language model is also still a math formula. In concept number 4, the last concept of this video, we'll see the actual equation used to update the parameters at each iteration of training. But that concludes our overview of training for now. Concept number 2 is linear regression. This one will take less time to explain. The super simple model we talked about earlier actually has a name, linear regression. Here's the equation again. This model factors in 3 pieces of information about the input person, x1, x2, and x3. But if we wanted to factor in more characteristics about someone, we could add more terms. And there is one issue with linear regression though. We can't square or raise to any power any of the inputs. And we also can't use any nonlinear functions, like the sigmoid function. For many cases, linear regression is effective, but sometimes the relationship between input and output is more complex. And in these cases, linear regression yields poor accuracies. But what if we just ran the training algorithm for more iterations? In those cases, even if we update the parameters repeatedly, the model's accuracy will remain low. Fortunately, neural networks solve this issue, which brings us to concept number 3. Neural networks are another kind of model, and they're much more powerful than linear regression. Here is a standard neural network. They use linear regression as well as nonlinear functions like the sigmoid. The 3 input nodes store x1, x2, and x3 respectively. Each of the 4 nodes in the next layer actually uses this equation. Each node in that layer stores its own set of parameters, which are w1 through w3 plus the constant term b. Those parameters are updated during training. Just to be clear, that's actually 4 parameters per node in this middle layer for a total of 16 parameters in that column of 4 nodes. But here's where neural networks differ from simply having each node do linear regression in parallel. At this point, we have 4 y values, y1 through y4. And before passing those values on to the next and final layer, let's pass each y value through the sigmoid function. Here it is again. Its outputs are always between 0 and 1. The larger the input, the closer the output is to 1. So what do the 2 nodes in the output layer, which we'll symbolize with the letter O, actually do? They use this equation. But the x's, or the inputs for this layer, are actually the outputs of the sigmoid function, which transforms the previously calculated y values. Just to be clear, here's the relationship between the y's and these x's. Each of those two output nodes learns and stores its own set of parameters, w1 through w4, plus a constant term b as well. That gives us two output values from the model. Let's simply take the average of them and report that number as the final height prediction. And here's the bottom line. Adding nonlinear functions in between the linear regression layers is powerful. The model is now capable of learning a far more complex relationship. That brings us to concept number 4, the actual equation for learning. The equation or algorithm is called gradient descent. Here are the formulas used at every iteration of training. Don't worry, no crazy calculus needed here. Also, the same formula is used to update w's and constant terms b, so we can just write one equation. Alpha is called the learning rate. It's typically a value like 0.001, but it can vary. And the derivative of the error is called the gradient. We subtract out the product of alpha and the gradient at each iteration. And with enough iterations, the parameters will eventually stop changing. At this stage, the model's error function is minimized. That's actually the main idea. This equation or algorithm, gradient descent, can be used to minimize any function. In this case, we use it to minimize the error function, specifically the error between the model's predictions and the true answers. The higher alpha is, the higher the product is. So we are subtracting out a greater number at each iteration. Higher alpha will cause parameters to change quickly from iteration to iteration, and vice versa. That's why we call it the learning rate. We want to find a sweet spot for alpha, and it depends on the model we're training. But why exactly does the derivative of the error function come into this equation? I actually have a separate video to visualize this concept. It's only 3 minutes long, and I promise it's worth it. It should pop up in the top right, and I really recommend checking it out right now. Really, right now. It'll also pop up at the end in case you don't click it right now. Okay, that wraps up our 4 must-know concepts. If you're still watching this video, I think you're the kind of person that would love our ML community. Check out the link in the description to learn more about it and to grab the free LLMs course I created. It's over 10 hours long with 25 different modules and practice problems. Let me know if you have any questions, and I'll see you soon.